To jump now to Fraser Lewis. I saw that I'm not going to introduce you, Fraser. Everybody knows you and you many times. So I think you can introduce yourself if you need, but I let you the lead right now. Thank you.
Okay, you see the slides okay?
Yes, we do.
Fantastic. So yeah, okay, the talk with no introduction. Okay, let me start. I will try and finish in 20 minutes because I know how bad a chairman I was earlier. So I'm Fraser. I'm based in Cardiff. I work for the Faulkes Telescope Project. I also work for the National Schools Observatory, which is the outreach and educational group attached to Liverpool John Moores University and the Liverpool Telescope. And I also work for the Open University. So I've got 3 separate hats that I can wear, all of which have robotic telescope on them in some shape or other. I have to thank all these people because all these people have put some talks together this week that I don't want to go over any of that material again. So if I miss out stuff, I'll try and answer questions at the end if we have time. But have a look at these talks if you haven't already seen them. Both Andy and Sarah gave excellent keynotes on the weekend. Stacey and Jenny gave a couple of really nice workshops on the different activities that NSO provide. I think maybe more importantly were the talks from the teachers. It's very easy to come along and tell you what a great project I work for, but to have teachers like Kevin, Alvaro and Philippe who come along and tell you what a great project I work for is a much better way of playing things. They're the people that are actually teaching the kids and working with the kids and feeding back ideas. So it's their work that really allows us to make progress. Here's an image. Every talk should have an image of a telescope or set of telescopes. So here's my one. Faulkes Telescope is the small set of buildings towards the bottom of the image. I kind of need to do that Men in Black thing on you right now because the rest of that is US military. So you didn't see it. It didn't get broadcast on Facebook. It didn't end up on YouTube, but that's US military anyway. So anyway, let's move on hurriedly from that.
Fraser.
Say again?
We're recording this.
We're recording this. Now you tell me that wasn't in the contract. Never mind. I didn't say anything bad about the US military. I just said that it was US military. Well yeah, okay. This is the Liverpool telescope on the left-hand side. It's not in Liverpool, as you might imagine. Andy explained very eloquently the other day why that would be in terms of the weather and the climate and the conditions in La Palma, where those telescopes are. These are all 2-meter telescopes with access to the Las Cumbres Observatory. We have access to a range of 1 meter and 0.4 meter aperture telescopes as well, many of which are able to produce really pretty pictures. It's a nice combination, I think, this one of science and pretty picture. It's the Crab Nebula. Many people recognize that. We look at the colors in there. It tells us a little bit about the chemistry. And when we zoom in on the center of this image, particularly in other wavebands, we find a pulsar, a rotating neutron star. So this is a supernova remnant. It's the aftermath of a 1,000-year-old explosion of a star. So we have supernova in this image and a pretty picture, which is fantastic. Another pretty picture image. I think these are where we start in astronomy. These are the questions. These are the things that cause the questions in people's minds. It isn't necessarily the graphs or the equations initially. So this is an image, zoomed in image of the center of a galaxy called M51. It looks quite similar to the way we believe our Milky Way looks. So a couple of pretty pictures there, and now we'll jump into a few graphs and bits and bobs in a few minutes just to make things a little bit trickier for those of you that are struggling already. Here's a really nice image. I think this one was shown earlier this evening by Alvaro. The image on the right is an image from our telescopes of a galaxy called Centaurus A. This is a really interesting galaxy for many reasons. Many different types of astronomy, many different branches of astronomy are interested in this galaxy. It has amazingly large radio lobes. It has X-ray emission from jets. It has a black hole in the center, which I think is of the order of about 1 billion times. Start again. I think it's of the order of about 1,000 times larger than the black hole in the center of our galaxy. So this is a very extreme galaxy. What was very nice, and Alvaro's image captures this very well on the left-hand side, is that we actually had a supernova that went off in this galaxy a few years ago. And Alvaro and his group were very active in trying to get data from this object. So it's that perfect combination of science and a pretty picture and a supernova. So we've got all these little bits coming together, which is really, I guess, what my talk is focused on today. I put this in. I know Rosa shouts at me for this slide, so she'll be shouting at a wall somewhere right now, going, "Ah, he shows the slide. He shows the slide again." Astronomy often is not that easy to squeeze into the curriculum. It's in physics. It's a small part of physics, depending on which educational board you're working with, what level you're studying physics at. However, we can be sneaky with astronomy, and we have to be resourceful. We can teach a lot of other subject areas through the medium of astronomy. That's something that I think we're all agreed on. I think we're all working towards. So astronomy can incorporate areas of maths. We can kind of sneak the maths in without the kids spotting it. We can certainly talk about IT. We can talk about geology and geography, particularly when it comes to the solar system. All these chemical elements, especially when we do spectroscopy, they feature chemistry. This is what chemistry is the study of elements, right? And then when we start to think about exoplanets, planets orbiting other star systems, that invokes this idea of biology. And we heard from Tony Thompson earlier today about the idea of how we study the Earth to maybe understand a bit more about what's going on in our solar system and perhaps further apart again, further afield again. One thing we're very keen on, and we can use something like GEHU as a launch pad for this, I think, as well, is to get schools to collaborate. And if we can do that internationally, I think that's a very positive thing to be doing as well. A really nice example of collaboration, and I guess as well, the reason for collaboration is this light curve and this set of images from about 8 years ago now. And this is a set of schools that worked on the imaging of the change in brightness of an asteroid. I should have had a potato from the kitchen. It's too late to go and get one now. But as an asteroid spins through our solar system, it reflects different amounts of light, and we can measure that. And this is the sort of graph that we come up with. On the x-axis, the horizontal axis, we show time. On the y-axis, the vertical axis, we show the change in brightness of this object. And to an astronomer, that's a sine wave. We talked about this the other day. Astronomy is not, I hate to say it because it's probably a wrong state. It's a very sweeping statement, but astronomy sometimes is not that accurate a science. Sometimes we end up with data that doesn't quite look the way it looks in textbooks because it's real data and has uncertainties and bumps and wiggles and all sorts of things in it. And this is an example of a sine wave or rotating light curve from a rotating asteroid. The reason I'm showing you this, aside from the fact there's a really nice sort of GIF going on the left-hand side, is the data there is taken or was taken by different schools. And those schools came from different European countries back when we were part of Europe. Each individual set of data doesn't necessarily tell you the full story. If you look at Poland and France and Portugal and Ireland, they contain elements of the light curve. They contain a fraction of the overall data. And this is something that we know from astronomy. The more data you can piece together, the more you can collaborate with your partners, the better the picture becomes, the clearer the picture comes. So it's, you know, it's almost a philosophical lesson, I guess. I don't want to oversell it, but the idea of being able to show data in this format is very, very useful to present this work where the schools were able to collaborate. So these were school taken images. Another really nice example, and again, it displays this, these sort of technical bumps and wiggles. This data is not as clear cut as you might imagine. This was a set of data taken by a couple of students that we worked with a few years ago again. This data was taken, or these data were taken in 2012. So this is only 20 years after the first discovery of exoplanets. So until 1992, we knew exoplanets would be out there. We figured they would be, but we didn't have any solid evidence. This is showing the light curve, the dip in light from the star as the exoplanet goes across the face of it. Like I say, there are bumps and wiggles in there. But these guys, these two students we worked with, they found a target. They found a suitable exoplanet. They took the data using our telescopes. They analyzed the data using free software. They plotted the data on Excel. So they did the full package. There are another couple of nice examples here. This is work that was done by undergraduates. You'll see a theme here. I'm not really presenting any of my own work at all today. I'm presenting lots of other people's work. I'm not claiming it as my own, but of course, if I get any nasty questions at the end, I can run away and say, well, no, I didn't take that data. The bottom graph maybe is the first one to look at, the two graphs there. The one on the right-hand side, again, you see this sine wave. Sine waves, when we see them in astronomy, they denote one of two things. They either denote an orbit of two things around a common center of mass, or they denote an object that is spinning on one or more axes. In this case, this is a binary star system. So this is a pair of stars, and they're orbiting a common center of mass. I can't do it because my hands don't really work that way, but you can kind of hopefully see what I'm getting at. Whereas one star passes in front of the other, so you lose light. And then as the two stars go side by side, so you gain the light back again. So this was data that was taken using our telescopes, and we were able to capture data on a series of different types of eclipsing binary systems. Astronomers being astronomers, if you give us 3 or 5 or 10 of something, we split them into groups. And so there are different types of eclipsing binary system, and we've managed to collect data on all of them, or the 3 main types at least. The top graph takes a little bit more thinking about. I'm not sure if I'm going to have enough time. I don't know if I can do this justice. The idea is here that we took multiple images of the same star. Now, this isn't a star or pair of stars that are orbiting a common center of mass. This is a pulsating star. Many of you will have come across the idea of a Cepheid variable star. The RL Lyrae are a slightly smaller scale version of the Cepheid variable stars. So the RL Lyrae star is pulsing. It's basically, it's going towards the end of its life, and it's just struggling to sort of stay on the main sequence, or just migrating off the main sequence. These set of images, now again, trying to describe what's going on here, the brightness is on the y-axis, this axis here, and the color, the temperature of the star, is on the x-axis. What this tells me is that multiple images of this star, it's behaving slightly differently in each one. There is a very definite trend line in there, which is from top left to bottom right. And it says basically, the hotter this star is, the brighter it is. So the redder it is, the blue, sorry, start again. The bluer it is, the brighter it is. When it's cool, it's red. This star is obeying Vine's law, which is reasonably encouraging. It's reasonably satisfying to find that out. But it's another nice little sort of project that we were able to pull together. On occasion, we've been able to get students to collect data with us, and we've put them in sort of proper refereed publications in monthly notices for the Royal Astronomical Society, Astronomy and Astrophysics. I need to update this slide because there are another 3 or 4 that I should probably add in there for completeness. I'm going to jump projects. So I've been talking really so far about the Faulkes Telescope Project and the data we collect there, but we incorporated that data into a series of other projects that now exist on the website, the link that you'll see at the bottom there. So I've created a few of these. We call them teacher-free activities. I run the risk of upsetting teachers, but the idea is that we can provide all the information and all the resources within a project, an activity project, that the students can go at in their own pace and to the depth that they choose. This project would take perhaps 10 hours, 12 hours to work through, but there are multiple data sets. The idea is that we give you more than one data set to work through. So, you know, you could work on this project reasonably solidly for 2 to 3 months. And at the end of that, well, go find some more data and take some more data using the telescopes and add that into the project. I'll be discussing these in quite a bit more detail tomorrow. I've got a couple of workshops around about 6 p.m. UT tomorrow evening. So if you're signed up to those, I can discuss those in more detail then. There are 3 of these that exist so far. So the first one looks at open clusters and the color magnitude diagram, or the Hertzsprung-Russell diagram if you prefer. This second one scavenges data. It takes data from this website called exoplanet.eu, which is everything you ever wanted to know about all the existing exoplanets and more. each of these exoplanets has multiple parameters: its mass, the orbital period of the system, the mass or the temperature of the host star, and so on. So we use this to plot different parameters against each other and see if we find trends. You can argue in this instance there's not much of a trend going on, but we have an activity designed around a population study of these exoplanets and what that might tell you. And I appreciate I'm nearing 5 minutes to go, so I'll keep going. I'll keep going till the point where I get told to stop. We have a new one. We had some extra funding earlier this year to dip our toe in the water of citizen science. So to try and look at these activities that I guess are in reality for 17 and 18-year-olds, 16-year-olds. It's the older group. It's the more independently minded students. But we're looking to see whether there are aspects of this that we can pull into citizen science. The idea that we provide lots of tools and we teach a little bit of science along the way, but we get data processed or worked on for ourselves. This one, I think Carl's listening, so I should mention it anyway for sure. This takes type 1a supernovae. Again, we've taken all the supernovae we know of and made them into lots of different types, but the 1a's are very interesting for a particular reason. We've put lots of background information in there. We show the students or the citizens how to use a photometry tool. So again, we've spoken a lot this week about Macaulay and Salsa J and JS9. JS9's online. So it gets around those horrible issues about downloading downloading software onto your machine, particularly when IT people won't allow you to do that. So JS9 is an interesting sort of pilot or case study of how we might be able to do that. We've created some Excel sheets with templates, so you actually put your data into them. It's a little bit of a black box, and we're careful that we don't make it so much of a black box that you just get the answer and no understanding of why. If you measure these supernovae, this is work that led to the Nobel Prize about 20 years or so ago, you can calculate the distance, you can calculate the expansion of the universe, and from that, the age of the universe. There are multiple steps. I can't really go through that in a 20-minute talk, as you might imagine. But again, what we're trying to add into this is, well, you know what, if you've collected or you've worked through our data, why not use the telescopes to collect your own data sets? It gives you a little bit more ownership of the project because you're adding your own data points onto existing graphs.
There's 2 minutes left.
2 minutes. Wow, I make it 3, but okay. Right, so we're using the Gaia telescope as a source for supernovae. We are creating light curves that look a little bit like that, suspiciously straight. We are then able to calculate the Hubble plot, and again, you'll be familiar with this from the work of Edwin Hubble in the late 1920s, which gives you a value for the expansion of the universe. What else can we add in? Well, we need to understand stellarium because we need to find out where these targets are in the sky. Maybe we can use Python. We saw really good examples earlier in the week of how to use Python in astronomy. We need to analyze the data. We need to use Google spreadsheets to maybe share the data amongst students. There are transferable skills in here. This is the key, I think, that we're allowing students to gain an insight into the scientific process. We're throwing things like logs and error bars in there that they might not spot because that's a maths thing and they don't like maths, and we're allowing them to develop their own projects along the way. Are there problems? Yes, there's more than one screen's worth of problems, but that's a sample there of the problems that we have in terms of providing the right amount of data and having students that are mature enough to understand that they have to make their own way through these programs. If you're interested in the Faulkes Telescope Project, you can register for free. If you're UK and Ireland, follow the top link. If you're Spanish, you can contact Naira Rodriguez at the IAC and you can get time on the telescopes that way. Anywhere else, email me and I can come back to you. And Manuel, you just came on the screen, which means you've got to stop me, so I'll stop there. Thank you very much for listening. I hope you enjoyed the talk. If you have any questions, then by all means, fire away.
Yes, thank you very much, Fraser. It's always amazing the number of things we can. And I very appreciate how you always say that it's not only astronomy, it's also a lot of knowledge and aptitude that we learn. And for this, we don't have time for questions as usual, but you have one question in the question and answer.
Sure.
You want to look at it and answer separately.
I'll have a look in a minute. Yeah, I'll just have